All right. Good afternoon, everyone. My name is Rupak Karan, and I'm a PhD candidate in the Department of Plant and Soil Science, working with Dr. Wanjan Go. And I'm also serving as the president for the PSS Grad Council. So today we have a graduate student speaker for the PSS Spring Seminar, Nicholas Boogades. Sorry. So Nick is a PhD student in Dr. Katie Lewis' lab, and his research focuses on carbon cycling and greenhouse gas emissions in regenerative cotton cropping systems. He graduated from Texas A&M last summer with his master's degree, also with Dr. Lewis. Before coming to Texas, he received his bachelor's degree at the University of Tennessee. Nick is originally from Edgewater, Maryland. So please help us welcome Nick to share his insights and expertise with us today. Thank you.
Awesome, thank you. Hopefully I don't take up too much of your time today, but we'll see how it goes. As I said before, I'm Nick. I'm a PhD student in Dr. Lewis's program. Just started last August, but I've been taking mostly greenhouse gas measurements for one of our projects, focusing on carbon cycling and regenerative cotton cropping systems. Much of the data I'll present for you today is greenhouse gas data, specifically carbon dioxide, but we're going to get into some of the idiosyncrasies of how carbon acts in different cotton production systems here in the Texas Plains. So a little introduction to the region, even though I'm pretty sure all of you are very familiar. This region produces about 1/3 of the US cotton bale production every year, and we do it in a very difficult climate. It's very hot. Our average temperature throughout the year is oftentimes very close to 60 degrees Fahrenheit, and we get very little precipitation, usually between 16 to 24 inches. And the use of conservation practices is very low in this region, with about 8% of acres utilizing cover crops and 37% utilizing conservation tillage, respectively. So all in all, this creates a lot of challenges for the region. It's a challenging climate all around. We have sandy soils with poor fertility and low organic matter, which makes it very hard to build soil organic carbon. There's a lack of conservation practice adoption, and producers and researchers in this region are challenged with the task of meeting the demands of sustainable production, which for semi-arid cotton production is very poorly defined. But we're not only working on trying to come up with a definition for sustainable production, but also trying to solve those challenges as they appear. So our main question we're going to look at today is how, or the role of regenerative practices in the future of Texas Plains cotton production. So a little overview to the project I'll be talking about today, or one of the two projects I'll be talking about today. It started out with a grant written by Dr. Lewis, Dr. Burke, and several other professors throughout many institutions from the Southern Plains region, spanning between northwestern Texas and western Oklahoma, with the goal of filling in the knowledge gap of regenerative agriculture in the Texas or the Southern Great Plains region as a whole. As I said before, we don't have a really great understanding of what regenerative agriculture is and how to increase adoption and what the outcomes of increased adoption in the region will be. So some of the challenges that we anticipate in the region that we think regenerative agriculture can address is going to be helping out with the depletion of water resources, using water more efficiently and mitigating depletion of those resources. Diminishing soil carbon storage is something that we're anticipating as well. We're trying to build soil carbon. We expect a net positive increase in greenhouse gas production if things stay the way they are, which of course will increase climate change. And then all of that could result in diminishing profit potential. So this project seeks to address these 5 main challenges with several different objectives. And so the overall goal of the project is to intensify agriculture production in an environmentally sustainable manner that enhances agronomic, economic, community resiliency in the Southern Great Plains. And the collaborating institutions for this project were the Texas Water Resource Institute, Texas A&M AgriLife Research and Extension, Texas A&M, Oklahoma State, Texas Tech, WT, the Soil Health Institute, and the overseeing partner, Kansas State University. So getting into regenerative agriculture and what it looks like for our region, when we started out, we didn't really have a definition for this project, but Dr. Lewis, Dr. Burke, and a fellow PhD student in the program, Chris Kobos, came up with a definition of regenerative agriculture specifically for our region. And that definition was the continued capacity of agricultural systems to function in a changing climate that supports soil health, communities, economic output, environmental sustainability, and resilience to the outside threats of these outcomes. So when we say regenerative agriculture, we consider that to be anything that provides to those outcomes. And specifically, some of those practices in our region that we utilize to obtain those outcomes are going to be cover crops, crop rotation, and reduced tillage. All three of these production practices come with some sort of benefit, whether it be water storage, providing a nutrient source, or better managing our nutrient sources, and soil stabilization. And the project identifies all three of these specific areas and more, but what specifically I'm focusing on in this project is the impact of regenerative agriculture on increasing soil organic carbon compared to conventional cotton production. But a lot of times what we see throughout years and years of research in the region when it comes to conservation practices and how they increase soil organic carbon is that our carbon accrual rates are actually very low. And today we're going to talk about why that is. So first of all, I'll give you a little background on the global carbon cycle. Soil is a major carbon reservoir, but it has the potential to be a sink. So a reservoir and a sink are two different things. A sink is a place to store carbon where it will stay there long term, whereas a reservoir is more of a storage location where the inflows and outflows of carbon are more balanced. So in a sink, you can place carbon there, it'll stay there for tens or hundreds of years, but in a reservoir, it just may stay there for 10 or less years. And our goal is to create a sink from our soils in the semi-arid Texas Plains region rather than keeping them as a reservoir. So if you look at carbon throughout the entire Earth system, we have photosynthesis. Well, specifically for soil, we have photosynthesis, which is going to be an input of carbon, and that's about 20 gigatons of carbon per year. And then we have respiration at a rate of 60 gigatons per year, and then decomposition at another 60 gigatons per year. And if you do the math on that, that comes out to net zero. And that's what makes soil more of a reservoir, is because we have our additions equaling our losses through respiration and decomposition. And we're just trying to balance those things in our systems, or create less of a deficit and more inputs compared to our losses. And how are we going to do that? Well, one of the ways we can do that without necessarily increasing the amount of carbon we're putting into the systems, or in addition to increasing the amount of carbon we're putting into systems, is making sure that we're adding carbon that will stay there long term. So labile pools of carbon have very high turnover rates and can be lost to carbon dioxide very quickly and may only stay in the soil for a few years. However, stabilized carbon, whether it's stabilized via chemical form or because of physical means, being physically protected in the center of a soil aggregate, that can reduce our carbon dioxide emissions and increase the amount of net carbon sequestration that we have in these systems. So here's a little graphical depiction of what it might look like in a cropping system, or a cotton cropping system specifically. We'll have the plant photosynthesizing, creating above ground and below ground biomass. We'll have root deposition and root litter deposition, which would act in that really fast or labile pool, and that'll very easily be lost to respiration. We also have crop harvest, which will be removing carbon and putting it into products rather than contributing to the soil organic carbon. But we also have slower and more passive pools, which could be things like lignin and cellulose in the cotton stalks that are going to be turned over much more slowly and have more of a likelihood of increasing the amount of carbon we have in the soils. And all of that can be managed differently by the amount of water, heat, and some of our management practices. I'm sure many of you know that specifically fertility, if we're adding a lot of nitrogen to the soil, that can cause our C to N ratios to be a lot lower in the plant biomass that we're creating. And that'll make it easier for that biomass to be lost to CO2, because microbial biomass or microbial respiration is going to be promoted when we're applying a lot of nitrogen along with our carbon inputs. And of course, the interaction between all these factors is going to play a very large role in how carbon is cycled in these systems. So our question is how do these regenerative practices affect specifically the losses in our semi-arid systems? So a quick overview before we get into it for anybody who might not be working in cotton here. This is our traditional cotton production timeline. So for a conventionally tilled or a conventional cotton system, we're going to have a growing season from about May to November. And then we'll have a fallow period just after harvest to right before planting. But in some of the conservation systems, specifically a cover crop system, we'll have the same cotton growing season, but we'll try to squeeze in a cover crop somewhere between, usually we'll try to plant right as soon as we can after cotton harvest, and then we'll have to terminate somewhere within 8 weeks or greater before cotton harvest. And we can manipulate these systems a little bit differently depending on what our specific goal is. And the way we manipulate the system is going to have could have drastic impacts on carbon cycling in the system specifically. So the objective of the main study we're going to talk about today, again, was to quantify the impact of regenerative practices on carbon cycling and net carbon balance, specifically looking at carbon dioxide fluxes. So this study took place in Lamesa. It's about an hour south of here. It's an Amarillo fine sandy loam, and the monthly temperature is going to be very similar to here, of course. This was done under center pivot irrigation with 2 different irrigation levels, 60% ET replacement and 30% ET replacement. And the systems we were looking at were a continuous cotton with winter fallow, winter fallow and conventional tillage. We also had a cotton with rye cover crop with reduced tillage, and then a cotton wheat fallow rotation, again with reduced tillage. And the measurements that we took, we had CO2 flux measurements done approximately monthly from June of last year to February of this year. We took some cover crop biomass data, and then we analyzed it in SAS, and I have some soil data to share with you as well. So just a little bit more on the specific systems. This is going to be your basic conventionally tilled system. Here is a picture of the cover crop system, and that matches the timeline that I showed you in the other graph before. And then the cotton wheat fallow system is a little unique. We have it replicated twice in these wedges here, so that in one phase we'll have, this was wheat that was harvested last June, and it'll be planted to cotton this year. And then this is the actively growing wheat. I think I took this picture a little over a month ago, and this is the wheat that's growing in the other wedge right there. This rotation, right after cotton harvest, we're going to plant wheat just like we would a cover crop. It's going to be harvested around June, and then it's going to have about a 9 to 11 month fallow period. The CO2 measurements that we took, we used a closed loop system. So greenhouse gas emissions from soil are diffusion driven. That means we can measure them passively with a closed loop system using a chamber and an analyzer. So as these gases are diffusing from the soil, it'll go into the analyzer, get measured. The specific instrument takes a measurement every 20 seconds. It'll feed it back into the chamber system here. And what we're actually measuring in each of these systems is going to be the buildup of that CO2 concentration every 20 seconds. So each of these dots is going to be one of those measurements. We're going to take the slope from about this green dot to this peak up here over the course of about 8 minutes. And we're going to measure the slope of this line, and the slope of that line will directly relate to the rate of carbon dioxide diffusion from the soil into the atmosphere. So getting into our data, this first set of graphs here is going to be looking at carbon dioxide flux rate. So the rate that it's leaving the soil in pounds of CO2 carbon per acre per day. The top graph is going to be that 60% evapotranspiration replacement. So our base irrigation level, and the bottom is going to be low. That's about half of the irrigation that this other system received. So the first thing that probably pops out to you is that this green line right here, which represents the cover crop system, is consistently, for the most part, our highest emitter just about until our last measurement here in February. And then you'll see that the second is oftentimes this maroon line right here, which is going to be the rotation that was in the cotton phase. Overall, you see that those two regenerative systems are going to out-emit our fallow system and the conventionally tilled system. And that's going to be because we have a lot more carbon input in those two regenerative systems. So we have a cover crop being terminated and decomposed by soil microorganisms in the rye system, and then we're also having the additional application of the wheat herbage mass in the rotation system. But you'll also notice that there is a lot of times there is actually a difference between the green bar, which is the rye, and the maroon bar, which was the rotation. And that's going to be due to the nature of the biomass input. So terminated fresh rye biomass is going to have a much lower C/N ratio than senesced or harvested wheat stubble. And that's gonna, as I said before, with the fertilization aspects of CO2 emissions, a lower C/N ratio is going to prime the soil microbial community a lot more. They're going to be a lot more active. And so that carbon that's added as rye biomass is going to be decomposed much quicker than that wheat stubble with a higher C/N ratio. Pretty much the same story here in the low system, except you'll notice that our emissions are a little bit lower, and that's just because microorganisms are just like us. They need water to be active, and when they're not getting quite as much water, they're not going to be as active and not going to respire as much CO2. But overall, it's about the same story down there in the low system, or in the low irrigation level. This graph will be looking at cumulative carbon dioxide emissions in pounds of carbon per acre. So the way we calculate these is you average the flux between two measurement days, and then you multiply that by the number of days between the two events. Up here is going to be the actual numbers on the four systems. So in the base, our highest emitter was the rye system at about 3,800 pounds of carbon emitted from June to February. And then in the low, it's going to be about 800 pounds less. One interesting trend you can see here is that the distribution of our different systems is actually a lot tighter. And I've seen that trend in some other studies we've done and that I did in my master's. And it's that when you add in something such as fertilizer, manure, or even irrigation, that's going to increase the capacity to emit carbon dioxide, so the capacity of those microorganisms, you're going to create a larger spread. So as we're adding more water, we're having a lot bigger spread between our highest emitter and our lowest emitter. But as those resources needed to respire are dwindled, everything starts coming a little bit tighter because your limiting factors in each system are about the same. So it's about water down here, a lot of it, and then up here it's going to be a lot about the carbon inputs and how those differ between the two systems. Another interesting thing is that you can see actually down here, there's no difference between our rye system and the conventionally tilled system. However, there's still a huge gap up here in the base system, and that tells me that as our water resources do dwindle here, and places that utilize the Ogallala Aquifer or just irrigation in general, our differences between conventional and regenerative practices aren't going to be as important, but that doesn't mean that we still shouldn't prepare for different scenarios. One other thing that can affect your CO2 flux is actually going to be when you terminate your cover crop. So we have another study going on within the rye system of the larger different system study down there in Lamesa. And with this one, we're actually terminating our cover crops at different times. So we have these plots here are going to be our fallow control plots, but we're also terminating our rye cover at 8, 6, 4, and 2 weeks before our target planting date of May 15. And so these images are actually going to be from last year, but the data they'll be talking about is from just the other day, actually on April 16th. So each of these red boxes is going to represent the plots for this specific termination timing. So 8 weeks are going to be these plots, 6 weeks are going to be each of these red plots, and 4 is going to be all of these. And then you can reference the previous plots in each preceding picture because they're of the same area. And what we're seeing is a really interesting grouping of our different termination timing. So just 2 days ago was when we terminated our 4-week timing. And I take my greenhouse gas measurements the day before we terminate. So this data is going to represent the 4-week plots before termination. So our previously terminated plots of 8 and 6 weeks, they're right around an emission rate of 14 pounds of carbon per acre per day. But our other two systems that had not been terminated yet and were planted to cover crop at the same date, they're around 11 to 12 pounds of carbon per day. And our no cover system is going to be a lot lower, just under 9 pounds per day. And that kind of represents it's going to be more similar to the conventionally tilled system in the other wedge just without any, or sorry, conventional cotton system from the other wedge just with no tillage. Getting into some of our soil carbon data. So this is actually going to be the soil carbon data from those three systems. So conventional, the cover crop, and then the rotation. And what we see is that overall, we don't have a total profile difference. And this is going to be our soil organic carbon from 2022. But we do see differences up at the upper depths. And that's likely going to be from our carbon increases from rye herbage mass happening mostly within the top 6 inches. And same thing with the wheat, but we're not really affecting anything at the lower depth. And we're actually seeing some increase at the bottom 24 to 48 inch depth in the conventionally tilled system. And the reason that we're not seeing profile differences despite increases in carbon additions is because those CO2 emissions from the regenerative practices are going to be so high. So if you look at the actual numbers, our above ground rye herbage mass is averaging about 1,400 pounds of carbon per acre each year. But if you look at those cumulative cumulative carbon dioxide emissions, the amount of carbon we're losing is actually double this number from June to February. And you might think that doesn't make any sense. It kind of doesn't, because we're not considering below ground biomass, which can oftentimes be just as much as above ground biomass. So if you double this, you get just under 3,000 pounds of carbon additions per year. And our C loss through carbon dioxide emissions was right around 3,000 as well. So that's really demonstrating how our soils are acting as a reservoir rather than a sink, because we're losing just as much as we're adding. Those differences are only happening in the top 6 inches, and we're not seeing full profile differences. With that being said, a lot of our nutrients and a lot of our microbial activity goes on actually at the top 6 inches. So that doesn't mean that there aren't benefits to only seeing increases in carbon at the top 6 inches. We're just not seeing total profile increases in terms of carbon sequestration. So next, we're going to look at some cotton yield. This is going to be from 2023. And we did have a fertility trial go on in these systems as well. So we'll just ignore that for now, and we'll talk about it a little bit later. But what we're seeing from a yield perspective is that we have a slight decrease in our cotton yields in the rye system compared to conventional, but we do see quite a big increase in the cotton wheat fallow system, especially in our wet years. This was a dry year, so our difference isn't quite as big, but this is typically our top performer when it comes to cotton yield. And in fact, most of the times we only get a cotton crop from the rotation once every 2 years, but oftentimes it'll out yield 2 years of either the conventional or the rye system. And if we look at some of our nitrogen use efficiency from the conventional system and the rye system, we are seeing that there's actually an increase in our nitrogen use efficiency in the rye system compared to conventional. And when we look more specifically at the fertilization strategies here, this is going to be a little bit older data from 2018 and 2020, I believe. And the fertilization strategies we're going to look at are a farmer standard practice of 134 kilograms, and then actually adding a little bit more nitrogen in these systems specifically to address nitrogen use from cover crop decomposition and see how that plays into some of our yield dynamics, because studies have shown that there is a immobilization deficit when it comes to decomposing cover crops, and that'll take up some of that inorganic nitrogen that your cotton really needs. So what we see is, again, that same trend where we have a lot higher yields in the rotation compared to the conventional system. But we also see that within the fertility strategies, adding that extra nitrogen is going to have a big benefit. So specifically in the rye system, where we're having that cover crop, that's going to contribute to immobilization a lot. So from the farmer standard practice, with the addition of an extra 34 kilograms of nitrogen before planting to help with that cover crop decomposition, we're seeing lint yield increases of almost 20%, which is going to be very significant from a farmer's perspective. And then if we look at the gross margins, we see a similar trend where that in the rye system, we're getting about an extra quarter on our gross margins. But another interesting thing to look at is that if we look at the system averages, we're having a 77% increase in our gross margins in the rotation compared to the conventional system, compared to the conventional system. So what this is showing me is that we can see some possible carbon benefits if we can figure out a way to keep the carbon that we're adding in from being lost, thinking back to the CO2 and the soil data. But this does have a massive benefit in terms of the economics for producers. So we really want to look more into this system and see how that can be of a benefit agronomically, since it's being so much of a benefit economically. Now we're going to get into a little bit of a different study looking closer at nutrient management, specifically and application timings to mitigate the immobilization of crop nitrogen, increase carbon, and increase our yields. So as I was talking about earlier, if we apply a little bit extra nitrogen during the initial decomposition of cover crop plant material, which we saw by that previous data, we might be able to mitigate some of those yield deficits we see with conservation practices. So just to put it really in perspective, our grass cover crops are going to be about a C to N ratio of about 26:1, and immobilization of soil nitrogen occurs at about a 25 to 30:1 C to N ratio. So we're right on the border of immobilization when we're talking about inducing immobilization when we're applying these cover crop materials. So the goal of this study was to make a few additional applications, either pre-plant or in the middle of the season, to help that cover crop to aid in that cover crop decomposition, and hopefully have some more inorganic nitrogen for our cotton crops. This study took place here in Lubbock at the AgriLife Research Station, and it was an RCBD design with the main plot being our tillage treatments. So we had two no-till treatments, one with a wheat cover, one with no cover, and then a conventionally tilled no cover system. And our subplots are going to be our fertility treatments. These are all going to be at 150 pounds of nitrogen per acre. We had a check with no nitrogen added, 100% added pre-plant, 100% added side dressed in season. And then we had a split, 40% pre-plant, 60% in season. And then we had 100% pre-plant with the nitrogen stabilizers. And as I said, all of them were applied at 150 pounds of nitrogen per acre. First thing we'll look at is going to be our soil nitrogen data. So this is going to be data from 2021 and 2022. 2021 is going to be on your left. 2022 will be on your right. Top is soil nitrate nitrogen, and the bottom is going to be total soil nitrogen. What we see is that we have that decrease that we anticipated in profile nitrate nitrogen due to immobilization and cover crop nitrogen use in the conservation system, specifically with wheat. And we see in 2022 much greater profile nitrate right before cotton planting compared to our conservation systems. However, if we look at total nitrogen, really just focusing on 2022, we see that our no-till wheat system has a lot more total nitrogen, and that's just going to be because we have input of wheat biomass, and that's going to be a source of organic nitrogen, and that's going to increase our total profile nitrogen. So we'll look at the impact of nitrogen timing, and what we see is that this side dress application, where most of the nitrogen is being applied in season, that's going to have the greatest amount of nitrate available right before cotton planting. That's just because you're applying nitrogen 1 year closer to planting of the crop the next year. And so not all of it's going to be used, and there's going to be more available for the preceding crop. And you see the same trend here if you look overall at the systems, much greater nitrate in the conventional system, especially for the side dress treatments compared to the no-till, and a really big reduction in the no-till wheat system. And then this one's always really interesting to me. Everything else is the same except for the side dress application in the no-till wheat system. So to me, that suggests that there might be those side dress applications in the no-till wheat system are probably affecting the cover crop somehow. And if you look at the cover crop biomass data, we do see that there's not a huge significant difference in terms of statistics, but to our eyes, there's a very clear bell-shaped here. And when we're applying that nitrogen in season, it's most likely providing a significant benefit in terms of the amount of nitrogen being applied in the organic form in these systems. So that gives a huge potential. You have a lot of organic nitrogen in this system that can become soil nitrate at the end of the year. and possibly be used as like a slow release fertilizer, which can be taken up by the cotton. So we'll see what that looks like in our yield data after we look at soil carbon. So this is, again, going to be from 2022 at 0 to 10 centimeters and 0 to 20 centimeters in our 3 systems. We have significant increases in the no-till wheat system over the conventional system in both the upper and the lower depths. The lower depths, we have no difference between the conventionally tilled and no-till system, as well as at the bottom depth. This was a study done by, I think he did it during his master's and his Ph.D. by Mark McDonald, and he also took CO2 measurements through this study. And what we saw was there is very similar CO2 fluxes between the conventionally tilled system and the no-till system. And so to me, that's saying that immobilization rates are probably going to be very similar because those CO2 respiration rates indicate that there's very similar microbial activity going on in those systems. And overall, that leads to very little difference in our soil organic carbon. All right, getting into yield, a quick disclaimer before we talk about it. If you remember, 2021 was a pretty good year. We had 20 inches of rainfall, and then in 2022 it was pretty dry. We only had 15. So 2021 was about perfectly average, and 2022 was to the lower part of our average rainfall years. And you'll see that that resulted in 2022 not having a lot of significant differences just because we didn't have enough water to see a real difference in these systems. But if we do look in 2021, both of our conservation systems had significantly greater cotton lint yield than our conventional system. I think a lot of that has to do with adequate soil moisture. If we get enough rain is when we really see these benefits of conservation systems. They can hold water better if they get significant rainfall in season. They are lagging a bit behind the conventionally tilled system early in the year in terms of how much stored soil moisture they have to establish a crop, but the conservation systems do a lot better of holding on to that water in season. So to me, that just says that overall, a lot of times, no matter where you are, you're going to have your benefits from conservation practices are going to be highly dependent on soil moisture. Looking specifically at our yield from a fertility standpoint, at our fertility treatments, I added the soil nitrogen data up here at the top just to give as a reference to our cotton yield to see if it follows the same trend. And interestingly, it doesn't follow the same trend. Specifically, if you look in the conservation or in the conventionally tilled system, our treatment that had the highest amount of nitrate at the beginning of the year was actually one of our lowest yielders. But if we go over to the no-till system, the trend follows more similarly to our soil nitrogen data. And then again, for the no-till wheat system, it follows it a little bit better than the conventionally tilled system is. But overall, we're not seeing a great link between the inorganic nitrogen because of the great amount of mineralization potential we see in the organic end pool in the no-till wheat system. So just wrapping up here really quick. Obviously, I didn't have a ton of data to present today, so I think I'm a little short, but I'll talk to you about the next steps of the projects and some of the other things we're going on. So I talked a lot about carbon dioxide emissions and a little bit about soil carbon. Everything we talked about was total carbon, but we are also going to be partitioning our soil carbon into different pools. So we have those active and stable pools that we talked about at the beginning, and some of those measurements that we'll be doing later are things like permanganate oxidizable carbon and potentially mineralizable carbon, which are going to be those active pools, and then some of those other physical fractions of carbon where they're physically protected are going to be mineral associated carbon. And we want to see the correlation of those carbon pools to CO2 fluxes. So if you have a lot more carbon in the active pool, you'll expect to see greater CO2 fluxes. But if more of your carbon is in that stable pool, you would expect to see your annual CO2 flux rates to be a lot lower. I'm interested in doing some crop residue analyses. We have a lot of ways to measure the activity of soil carbon that we just mentioned, but there's also some analyses that you can do on crop residues, such as how much lignin cellulose and hemicellulose are in those crop residues. But I'm interested in kind of trying to standardize those measurements by maybe running some of these tests that we have, such as permanganate oxidizable carbon that we do on soil, and actually running those on our crop residue to see if see what that difference is from a carbon perspective. When I talked about the rye biomass being a lot different than that terminated or that harvested wheat stubble being. And then I would like to also incorporate a little bit of below ground plant biomass, since that can be such a huge part of how much carbon is being added to these systems, sometimes greater than 50%. So I'm interested in not only quantifying that, but running some of the same tests that I talked about for the above ground crop residues. And then some other projects that we have going on. I'm not involved in all of these, but they're all incorporated to that first project that I talked about. I am involved in this study here, a grazing study in Vernon, Texas, where this picture was taken actually, I think a month or two ago. But that's going to be different grazing systems and different cotton systems, very similar to the ones that we were investigating in Lamesa. But this region gets a lot more rainfall, so we can do a little more interesting things with cover crops, incorporating some legumes and other things. So I'll be looking at carbon in those systems as well. The cover crop termination timing study is a really interesting one. That one's also going on in the Vernon area. Chris Kobos, our other PhD student, is the one that really heads up the cover crop termination study. He's doing some USAS measurements to try and estimate biomass using drones. And he's also has some really interesting moisture data that if you're ever at a conference and have a chance to check out his poster, I highly recommend that you do. We do have some on-farm components, so we're not only just looking at plot research, even though the study in Lamesa is about 100 acres or so, or just under 100 acres per wedge, and it's done on a large scale. It's also good to see how it's done on an actual producer's operation. And then quantification of other greenhouse gases. The instrument that I showed a picture of earlier that we use, it can measure hundreds of gases at once. So we're focusing on not only carbon dioxide, but nitrous oxide, methane, ammonia, and really anything we want. We can send off our data to GasMet and have them analyze it for whatever we'd like to see. So trying to see if there's any differences with other greenhouse gases in those systems. And with that, I'll cut it here. I used up about half your time, so I have plenty of times for questions if anybody has any. On the left, it's going to be our lab website if you want to check that out. And then that first project that I talked about has its own website that you can check out as well with some great information on it. So thank you all for your time. So that's a great question. The question was, how do I plan on collecting below ground plant biomass? I tried to do that a couple weeks ago. The ground was very hard. I tried to use a shovel, but I have found some methods where you can actually use a Giddings like we use. So maybe if we got a little bit larger soil core, not too much bigger, just to get a larger area, you can take a soil core, and then they have machines that can mechanically separate root material from soil. I think it's pneumatic. It might use some water as well, but I think it's hydropneumatic. So I've never used it before, haven't heard much about it, but it seems pretty effective. And one of the easier ways, I think less labor intensive ways that I've seen. So that would be how I'd plan on doing that.
So with all the carbon work that you've done, in addition to quality project, can you make a conclusive statement as to whether or not it is a cover crop or a crop rotation with cotton that's driving carbon sequestration, or do you have to have the tillage component, or tillage alone?
Yeah, so the question was, what's driving the carbon sequestration benefits? Is it tillage, or is it the cover crops, or is it the cropping systems? I think managing the decomposition is going to be a big part of it. From the air quality work, which is the second study that I presented, we actually did see that the no-till, no-cover system was inching closer to that no-till wheat system compared to the conventionally tilled system. Another difficult part of it is, I think you can do the research on all these different systems, but what is actually going to happen? A no-till, no-cover system is going to be very difficult. I don't know if you can do that in Lamesa, but we've also, Yeah, so from an erosion standpoint, I would say, I guess you could sand fight and try to do as little tillage as you can. Your cotton might get sandblasted if the ground isn't being broken up. We're able to get away with it in the cover crop system because there's something growing almost all the time there to break up the wind. The other component is I haven't been too much a part of research where we look at cover crop with tillage. So that would be something interesting to look at to really piece it all together. But specifically for each system in Lamesa, from the rotation, I believe it's coming from the recalcitrant carbon we're adding and the fact that our activity drops so low during the long fallow period. In the cover crops, or sorry, in the conventionally tilled system, it's just because we're not having priming of microbial activity. And then we're kind of just throwing everything at the rye system, it seems like. So it's getting that additional carbon to try and boost those carbon levels, but it is supercharging the carbon dioxide emissions. So it's really system dependent, I think. Chris sits in a truck with me for 6 hours at a time sometimes, so he gets all the answers. Sorry, go ahead.
There's a nice presentation. I just want to really say with the soil moisture and see the effect of different practices. But with the climate change we have here, we are getting more dry and dry and dry and dry. In the future, we're able to see those effects of these regenerative practices with the climate change we have here.
Yeah, so I think the question is, are we going to see how are we going to see the effects, or what will we see effects with the changing climate and changing water? I think it's more of a tool of fighting against those changes. So, for example, heat and evapotranspiration in these systems, the soil in the conventionally tilled system will get up to 135 degrees in the summertime because I take soil measurements, soil temperature measurements along with the greenhouse gas readings. But then the rye system always stays much cooler, maybe 5 to 10 degrees Celsius on a really bright sunny day. And that's really going to cut down on the amount of evaporation you're seeing from the system. So if we're getting less rainfall, we really want to cut down on our water losses. And keeping the soil a little bit cooler is going to help with that a lot, I think. Also, breaking up the soil is going to really, you're going to have a huge loss of water vapor with that as well, increasing evaporation. And then if we are increasing our soil organic carbon in these systems, we're going to, soil organic carbon has so many benefits. It holds onto water really well. It's a slow release nutrient source. And it just has so many benefits that buffer against changes from climate change. So, and Chris does have some data that shows some benefits to actual water storage as well from regenerative. So that's a great question, but we'll see. So hopefully we get some good climatic differences over the next couple of years during the study, and we can have some really good answers. All right, thank you.